I hope everyone's having a great evening. I am Mr. Ish. Thank you for joining me. In this video, we're looking at more ODE, ordinary differential equations. We've already presented a video on ordinary differential equations or the formation of differential equations. We'll just look at 3 examples in this video, taking an expression and generating a differential equation from that. Let our first question be y is equal to a sine x plus x. When you're looking at that, you have an expression which has a constant in it. If you were to eliminate this constant, you can generate a differential equation. Since there is a single constant, you can do one step involving a derivative procedure. And that's exactly what you want to do. When you take the derivative of this, you're going to generate a dy over dx. You know, that's synonymous with this y prime. And then you'll do the derivative of everything after that equal sign. A sine x becomes a cosine x. X becomes a 1. You have to solve and somehow get rid of that constant, and you can solve for this a and eliminate it in that way. A cosine x is equal to dy over dx minus 1. A is equal to dy over dx minus 1 all divided by cosine x. But you see how the cosine x here is in the denominator. You can bring it out onto the side and bring it as a secant x. Then you have a dy over dx minus 1, and you know the secant x is going to multiply with everything here in the numerator. Cosine x or its reciprocal, everything here seems good to me. You're looking here at an a is equal to all of this. Then here in this original equation, substitute this expression here for a. You'll have y is equal to that a, substituent coming into play. You'll have a secant x, then you have a dy over dx minus 1 all multiplying with the sine x plus x. You can open that up and then that would be the end of it. You'll have y is equal to secant x sine x, then dy over dx minus secant x sine x plus x. And this here can represent a differential equation which you could utilize. You could clean this out literally, because these secant x really represent, secant x here represents 1 over cosine x. You can bring the 1 over cosine x, impact everything with the sine x, and bring a tan x. Y is equal to tan x dy over dx minus tan x plus x. Remember, this right here is just a hypothetical expression. It could mean something practical, but we're just generating and utilizing this as an example, generating a differential equation, an ordinary differential equation. Take the y on the other side, you'll have a tan x dy over dx minus tan x plus x minus y is equal to 0. We have here a dependent variable, independent variables in terms of these functions, and then we have here a derivative of y with respect to x. So this right here is indeed a differential equation generated from right over here, and it's done. You can see how the procedure was. Here we just cleaned it up. Secant x sine x is the same thing as sine x over cosine x, which is a tan x, and that came into the picture. This question here is done, so let's just look at another one. How about this? Y is equal to ax plus bx. How many constants are there? There are 2, a and b. Therefore, you can do 2 derivative steps. You can do a derivative of this expression twice. The first time, dy over dx, you'll generate here an a plus a b, because the x's go away in each instance. You could have also done this in terms of this x into a plus b, and then you're looking at a derivative of this. It would still be a plus b. The x would have gone away. That's your first step right here. Then the second time you do it, you'll get this d square y over dx square. You're doing the derivative of this. All of this is constant, it'll become 0. And then basically you're left with nothing other than this as your differential equation. Your second order is equal to a 0. The question we saw before, that was a first order differential equation because only one constant was seeing a. This here is a second order differential equation because it came from an expression with 2 constants. And how can you tell it's second order? Because of this right here, or the presence of these 2's. It's second order differential equation. Second order differential equation. That's exactly what it is. Let's look at one more question, and I think we can be good with that one right there. Y is equal to ax squared plus bx. That is what we have to utilize and generate a differential equation from it. There are 2 constants involved, therefore we will have a second order differential equation come out of this. If you do the derivative the first time, dy over dx, you can have a 2ax plus b. But you see, we still have the constants involved. It would be helpful to do another round. We can do that. D squared y over dx squared is equal to 2a. This right here helps us out in terms of a useful expression. Wherever I have a 2a, I can substitute a second order with respect to y. I can do that. What I can do from here is solve for a. I'll have 1 over 2. I'll have d squared y over dx squared. I have that coming out in terms of a. And what I can do from right over here is solve for b. In this instance right here, I can solve for b, and I can also plug the 2a right over here. This 2a and this thing can come right over here. I'll have dy over dx is equal to d squared y over dx squared x plus b. You see, 2a got substituted for this second order with respect to x for y right over here. And now I'm going to solve for b from here. b is equal to dy over dx minus d squared y over dx squared x. Here is an item for b, here is an item for a, and these can all come right here in our original equation. When we do these two substitutions right over here, we'll eliminate the constants. Y is equal to ax squared plus bx. A is equal to this 1 over 2 d squared y over dx squared times an x squared, because I see an x squared over here, plus bx. B is this, and multiply with an x. dy over dx minus d squared y over dx squared x, but there's an x sitting right outside because it's a bx. You would have to open up all of this and just do a little bit of algebra, and you'll arrive at your differential equation. When you do this, you'll have an x squared over 2. You have a d squared y over dx squared. When you open this, you can multiply this with that, and you can multiply that with that. You'll have a x dy over dx minus x squared d squared y over dx squared. I'm seeing a couple of common terms over here. These two are common terms because they're attached to a second order derivative with respect to x for y. I have a minus x squared plus x squared over 2, which will be a minus x squared over 2, and then I have this. All of this, you know, is equal to this original y. Let's come right over and finish it up. Y is equal to, I'm going to write the positive term first, x dy over dx. Then the combination of these two, which is a minus x squared over 2 d squared y over dx squared. That right there is your differential equation. You could take the y on the other side and make it equal to 0, or you can leave it as is and it's just fine. Everything here looks good. If you want to write these in different notation, you can. You can say y is equal to x y prime, because I have a first order here, minus x squared over 2 y double prime, because I have a second order, and this can represent another differential equation. But in both instances, the constants have been lost, and that's exactly the purpose over here. To form that differential equation, you eliminate the constant. Just like forming a rectangular equation, you eliminate the parameters. Here you're doing something similar to that. And that's about all we want to show you in this particular video. If there are any questions, you can let me know. Have a great day. Bye.